My name is Harald Bouchoudis. I'm from Kio Center of Excellence at the University of Cyprus. Today we'll speak about SUMO-UAV-Py. It's a plugin which aims to, I think it succeeds to bring UAV-based sensing into SUMO. Integrated is what we made with Christos Makridis and our professor Stelios Timotheou. Our today's talk will be organized as follows. In introduction, we'll speak about the motivation behind the plugin. We speak about some gaps we located in the literature, as well as our contributions. Then we'll follow with the design and implementation of the plugin. We speak about the architecture, the models, some of the calculations we did for the field of view, and some details on that. And then we proceed with the user interactions, what feature we provide, how the plugin feels for the user, how the user can use it, and we'll provide a short benchmark of our plugin, and we'll finally conclude with the conclusion and the future works. Starting with the motivation, we see that as urban environments grow more complex, researchers need monitoring that is both detailed and scalable. And they need that to have more efficient urban mobility management. In the first sense, the UAVs can provide this dynamic and aerial monitoring of the environments and can bypass some of the problems that you have with fixed sensors like radars or loop detectors. But they do not come without limitations as well. They have some regularity and privacy problems as well. And we tried to use this plugin as an evaluation platform to have a better real-life test and have an evaluation testbed for that. The gaps we found in literature, we found a rich ecosystem of UAV simulators, but they mainly focus on flight physics, navigation, and even some swarm coordinations, multiple UAVs in a network. And from the part of traffic simulators, we don't have an explicit support for aerial or vehicle level sensing. And we have as well some co-simulation approaches for UAVs and simulators, but they do not offer UAV based in large networks. And they add to complexity and some microscopic data information as well, which we do not need. And our contribution is to provide an open source, lightweight Python plugin that we can integrate fully into SUMO, that will provide real-time vehicle level sensing from the UAV perspective. And this plugin is generally modularly configurable. We to provide to the user some options as well, and it's generally user-friendly. We tried to program it in a way that a non-Python user can configure and run the plugin as well. Now, starting with the implementation and the design of the plugin, we start with the inputs of what we give to the plugin. It's the basic SUMO network and the simulation parameters. It's all SUMO-related parameters. It's the network, the root files, the additional informations, and the part of the plugin which you have to define the number of UAVs we'll use, the waypoints, the positions of the UAV want to pass, the field of view information, and other informations. The plugin starts with the initialization, which launches the plugin parallel with the plugin with the TRAS interface. We do read the UAV parameters as well as the waypoints. The waypoints, it's basically depending on the model we will use, it's the locations of the UAV we want to pass, and we start the runtime loop. Here, the plugin will compute the UAV position at each step. It will update the position into SUMO with TRASI, and then we'll retrieve the vehicle states that we want that are located in the field of view. And the main output will be a microscopic UAV observations as we'll expect from a real life in experiment. To succeed that, we use this communication loop. It's a TCP connection. Tracy communicates with SUMO and the plugin to request vehicles, the vehicles variables we need, like the speed and the position. We send it to SUMO. The SUMO sends the vehicle variables back. We calculate the field of view. We calculate which vehicles are inside this field of view, and we use the subscriptions. So we have a better optimization in. It's really very fast relative to the conventional way. And the UAV updates, and we take the output file as well. Following, this is how we define the configuration inputs to the plugin. We give the network and we give the simulation configuration as well. This SUMO configuration file consists of the routes and the additional files we want to change. And from the perspective of the plugin, we can give the field of view in terms of degrees. It's what we get from commercial drones or the drones we use in our research institute. We can set the UAV speed. If we're gonna use a simple model with a linear approach, we can define as much as our performance allows number of UAVs, and we define the positions in a JSON file as we see there. And we also give the options for different modes. It's the hovering, sampling, and spinning. I will explain later in the later slide. Now the output file, it's the same. We tried to do it as similar as aerial drone. We do have the step, the seconds of the simulation, the ID of the UAV, the position, as well as the position of vehicles inside this field of view, the speeds, and it's kind of modular, can request more information if you want, but this is the initial state. Now for the motion mode, this is how the drones look like, the plugin looks like. This is a very simple model. It's the default model we give to the user if it wants to do a simple experiment with UAV. The basic serial approach is that the UAV rotates the target position. It moves in a linear way with the uniform speed we give, and then it rotates back to the final view angle. And this is the way we calculate the steps and the speed. And of course, we give the option to the user, if someone wants to calculate the path offline, give a more advanced path to the UAV, he can put it in this 2D plane and add it to the SUMO simulation. It will work just fine. This is for people that can calculate the UAV trajectory and add it to the plugin. We do give that options. And a brief explanation of how do we calculate the field of view. We get initially the degrees, and this is the transformation we get for the rectangle that we see in the previous slide. This is very dependent on the height and the angle, as you guys can see. And another geometric problem we solve on runtime is the rotation of the rectangle. We use this equation here. This is just the R in this function is just the rotation matrix. For more information, you can refer to the paper as well. And after calculate the field of view, we perform a visibility test. We calculate which vehicles are in the field of view, and we write it to the output file. And for the visualization, you guys see, this is just it is actually a part of Nicosia. We do not have a chaotic network system, so you guys can see. In reality, the UAVs are never synchronized like that, but for demonstration purposes, let's show something pretty. For the visualizations, we use the polygons tools. The field of view is represented with polygons. We set the coordinates there, and we visualize it like that. We also use the point of interest icons, custom icons for different models of drones, and we perform dynamic updates. In each step, we have the updated UAV position, and we update also as well the graphic interface. Of course, when the UAV it's not moving, it's hovering, we don't perform many updates for optimization of performance, and we can toggle off and on as in SUMO the representation. Now for the user interactions for our main course, we do offer 3 different UAV models. It's what we use in our research center as well. These are just 2 commercial models, but of course we provide a manual custom specification model, which the user can give different field of views, different speeds if it likes, and the other configuration settings. We also provide a very simple battery simulation option, which will give warnings, and we auto lands in depletion of the battery. And we have 3 observation modes in the first video here. As we can see, the field of view is constant, so as well we can see a field of view that means that the drone is observing. And in the sampling modes, we can see that graphically that the drone is only monitoring when it's stable. This is actually a more realistic approach, because when we see when the drone is moving, the monitoring is not that accurate. And the third option is just a spinning option, where instead of hovering, the drone is moving around. It's just we didn't find any use case for that yet, but we cover it. Sorry. Now we also provide some real-time interactions when we cooperate a parallel thread, when we can in the GUI interface we can say while the simulation runs, with this interface we can say to the UAVs to change positions on runtime. This use case for cases that we don't want to restart the simulation, you can do it on the fly. And inspired by this, by the interactions, we do provide a server-client interaction as well, when we have the main communication loop with Tracy and SUMO, and then we have an additional column where we basically open a server socket, which the user can use MATLAB, Python, or any other TCP comparable program to give and update the UAV positions on the fly. Is generally useful for people that do not want to use Python, or they are already simulation for UAVs, and they want to perform their own experiments. We are compatible with that. And finally, a simple configuration interface for the user can put the configurations in this setup, as you guys can see. And for the evaluation of the plugin, we did use the scenario of Bologna for my Tetris. It's a medium scenario. We just use 3 hours of virtual time, of simulation virtual time. I use my personal desktop for generalization purposes. And the methods we use is the plugin, where we use from 0 to 32 UAVs, different UAVs. It's the first method, and the second method, we use the FCD output from SUMO, and then we use an XML post analysis. Then we parse the same positions that we get from 32 UAVs, and the results we can see in the next slides. We do see that both methods are generally comparable, but without the full feature of the plugins. And with the red line, you can see how the plugin, the overhead of the plugin, it's quite high, and something we tried to fix and to improve the performance. But for UAV usage, the plugin can be a good approach for anyone that wants to use it. It's safe and scalable, I would say. Our conclusions, we see that the user can use the plugin to fully integrate it into SUMO without need to have any core simulation platform. We do provide a real-time microscopic sensing from the UAV perspective. The plugin is quite flexible and modular. We see that we offer some features that allows users that they do not want to use Python or customize it to use it, and it's generally scalable if we want someone to do UAV research. Now for the future work, we do want to introduce some constraints to the field of view. If you guys can notice, we assume that the pitch angle of the camera is 90 degrees. When the camera is not 90 degrees, we don't have a perfect rectangle, so it's something we can add to the plugin as well. We do plan to incorporate some microscopic measurements as well regarding density, flow, and average speed inside the field of view for different aggregation periods. And that can be useful because we can calculate them in a microscopic manner. And also it can introduce some advanced dynamics in the default model. We can integrate some high fidelity flight physics, and also write some our own trajectory planets. And the most importantly is for you guys to use it, to have some feedback and fix the bugs and general problems we have with the plugin. That's all from me. It's the plugin is open source. You can download it here, and this is my contact as well. Thank you.